Okay, why do we dry and cure? If you remove a flower, it won't burn, and if you store it, it'll go moldy because it's wet. So how are we doing it today? We're using air conditioners to put the flower in to remove moisture, and we're using dehumidifiers to remove the moisture. These are not process controls. This is comfort cooling equipment. So right now, the flower goes into a space with the air conditioners and dehumidifiers. And someone needs to guess when to arrest the drying process, because this equipment continually removes moisture from the flower. If it's left longer, it's going to over-dry. So we depend on people to know when, touchy-feely bro science. And is there a single person in the facility who has that touchy feeling? Is an entire operation depending on this one person? And what if we see the flower is going to be ready on Sunday? Do we have to bring in a crew on Sunday to remove it from the dry room, or we're going to sacrifice that flower because it's going to be over-dried on Monday? So, are we just wasting labor dollars here? So, what are we doing? We're stopping the drying. We're hopefully moving the dry flower into sealed containers. We start burping to remove unbound water. And burping in different areas, sorry, this is US centric, but it applies anywhere in the world, depending on the climate, the burping process. Yeah, so this goes back to the first slide, science or art. What are we doing here? So, some say the key is to control humidity, but humidity is relative. So, humidity is the result of two variables: the amount of heat in the air and the amount of moisture in the air. So, where the temperature, which is the blue line, and the amount of moisture in the air, the green line, intersect, the curved line is relative humidity. So people who say they control relative humidity, that means they can move the dot on this curved line. You can't. You can change the temperature, you can change the moisture, and the result is relative humidity. So a lot of people say, hey, I want to dry at 60% relative humidity. And here I show 60% as a solution many different ways. So the question is, which 60% do you want? Different temperatures and different vapor pressures or dew points solve for the 60%. So this is going to be interesting. We're going to do a thought experiment. We have a vessel, and it's going to be a sealed vessel. We're going to put a predefined amount of water in that vessel and seal it. There's the lid, sealing. Now that water has turned to a gas, and the relative humidity is 50%. I'm going to heat that vessel, the air in that sealed container. And look what happens. The relative humidity dropped to 20%. The amount of moisture didn't change. What we did is we warmed the air, and warmer air can hold more moisture, so the relative humidity went down. Here, we have two balloons. Both are 80% full, but have different amounts of water. And here, the same amount of water, but you can see different amount of volume. So the purpose of this explanation is, when you talk relative humidity, it really isn't very meaningful. And so now we're going to talk about the real science behind it, and that's vapor pressure and dew point. If we know vapor pressure, there was an equation there that if you know vapor pressure, you know dew point, or if you know dew point, you can solve for vapor pressure. So we can use the term interchangeably. So when we start talking about pressure, we can use the analogy of a tire. Does it matter where the stem is when you measure the air pressure? No, because the pressure equalizes throughout the tire. So people talk about vapor pressure deficit. So now we see the vapor pressure difference has equalized. So measuring moisture and vapor pressure is not new science. The food industry has used it for a long time. In fact, this technology we're using for cannabis now was first developed for cheese aging rooms. And the science is used in many different industries. So, when we want to dry a flower, and sorry for the Fahrenheits and not Celsius, but we want to get the product to a 14.2 millibar vapor pressure. If we move the decimal point one over, that would be 1.4 kilopascal. So, on a winter day, it might be relative humidity 80%, but the vapor pressure outside 2.86. And because the flower, a high vapor pressure, the moisture is going to go to the low vapor pressure. It wants to equalize, like the tire. Now, on a warm summer day, still the humidity is 80%, but the vapor pressure outside, 31.61, is almost greater than the flower. So the moisture is going to move to the flower. So here's how your dehumidifiers and air conditioners dry the flower. When the liquid refrigerant goes into the coil, the evaporator coil in the air conditioner or dehumidifier, it's going in with this vapor pressure, which is lower than this vapor pressure. So that's how the flower dries, going to the coil. And this is why if you leave the flower in a conventional dry room, it'll turn to dust. You have to arrest the drying process because the moisture will continually go from the flower to the coil. And here it shows why the construction of a dry room is so important. You have no control over vapor pressure as the weather and the climate changes because it's permeable. So, once we understand the vapor pressure, we can start talking about water activity. And water activity expresses bound and unbound water. The unbound water is free available water. And unbound water, the molecules are free to leave the flower. Bound water, they're tied up in the cell structure. It's the microbes, molds, bacteria that feed on unbound water. Once you remove the unbound water, you have a shelf-stable product. Mold cannot grow. So, once we get to a 0.6 water activity, there's no longer enough unbound water for microbes to grow. You have a shelf-stable product. Every molecule additional that you remove, you're removing a molecule of bound water. That's weight off the scale. And if you're in business of selling the product by weight, that's lost revenue. Here's the explanation of your bacteria, your molds, yeast. You can see once you get to a 0.65, they no longer can grow. There's no longer enough free available water. So anything below 0.6 that you dry the flower to is just lost revenue. It doesn't improve the quality. In fact, the smoke is a harsher smoke. And now we can talk about the revenue component. At 0.6 is at baseline. If you dry your flower to a 0.5 water activity, you've lost 5.6% of your revenue, top line sales. So some people talk about percent moisture, but the percent moisture doesn't talk about bound and unbound water. It's the total water in the product. So that bound water number is very important if you want shelf stability and to maximize yield, where percent water lumps them all together. So who uses percent moisture? People who sell firewood, lumber, hay. They sell their product by volume. People who use water activity, pharmaceuticals, food, and cannabis. And this is how, water percent moisture is done. I'm going to just move forward. So wet flour has a very high vapor pressure, and what we are talking about is putting that flour into a space with a controlled vapor pressure. At the vapor pressure you want the flour to come to equilibrium. So this is why we control vapor pressure. We like to call it sous vide for weed. Cooking sous vide is where you take a meat or a fish and you put it in a water bath at the finished temperature you want to cook that protein to. And when you cook that way, you can't overcook it. You can leave it there for hours. It just won't overcook because it's come to equilibrium at the finished temperature. And what we're doing is we're putting the flour in a space that comes to equilibrium with the vapor pressure, so it cannot overdry. And you can just leave it there for weeks, months. So no longer do you go from dry to cure to store. It's one continuous. Now, what we're learning is when you're maintaining a constant vapor pressure, we're preserving the trichomes. And that's the whole purpose of growing the plant. It's the trichomes where your THC, CBD, and terpenes are produced. So what we've learned is conventional systems using air conditioners and dehumidifiers, the vapor pressure fluctuates. And with that, we learned that traditional, using air conditioners and dehumidifiers, 20 to 30% of the trichome heads rupture. And by keeping the vapor pressure constant, only 1 to 2% of the trichomes were damaged. So that first study was done by counting damaged trichomes on grids under a microscope. Not convinced that we had good, solid numbers, we went to chromophotography. And we know that ruptured trichomes tend to turn red. Chroma, red, traditional. Our constant, no red over here. So this confirmed the grid count by going a completely different method to measure. And here we have a typical dry room, pink line vapor pressure fluctuating. This is maintaining a fairly constant other than some noise. And by maintaining constant vapor pressure and not having ruptured trichomes, you have about 16% higher terpene retention. So, having proper post-harvest control, you really have control of what is coming out, and you have many opportunities as far as better product, yield, and with all that, you can also hold the flour without loss of quality, which is very useful during price fluctuations in different markets. And we're also learning that different cultivars now, when properly cured, because before it was putting it in a jar or container, now we can hold it constant. We're seeing different cultivars can offer premium product with longer cure. So the different all the benefits now of what you get: higher yield, better product, reduced labor, speed to market. This gives you better SOPs, standard operating procedures, great for GMP compliance because you have control and repeatability, and you're improving your shelf stability because your trichomes are more stable. And cup awards. We have many users, and their secret recipe is they're using vapor pressure with one of our systems to win cups. Thank you.